Hello. At the end of today's lecture, we'd got to this stage in the handout where we were talking about nucleophilic catalysis. And we looked at these two examples of a non-enzymatic nucleophilic reaction just to show the effect of having a nucleophile held in exactly the right place. So in compound B, we have an intramolecular nucleophile, and we worked out that's equivalent to having a concentration of 2 × 10⁵ molar of the nucleophile, so a really high effective concentration. And this is the type of nucleophilic catalysis that enzymes can use. Very often, nucleophilic catalysis in enzymes is complemented by general base catalysis, as we'll see. And the example we'll look at is a sort of classic one of nucleophilic catalysis in enzymes, which is the enzyme chymotrypsin. So again, this is a protease. It hydrolyzes amide bonds, and again, just like thermolysin, it uses a BAC2 type mechanism, but it's rather more involved because it goes through an intermediate ester. We'll see exactly how that works. So the first thing that happens is that the compound binds to the active site, and what we find is that there's a selectivity with chymotrypsin for hydrolyzing an amide bond adjacent to a large hydrophobic residue. So this amide is going to be cleaved, and that happens because in the active site there's a hydrophobic pocket. So just as the name suggests, an empty area lined with hydrophobic residues into which this group can fit. Okay, so we have this sort of fitting into a pocket. Okay, and then we hydrolyze this with a molecule of water to 2 products, a carboxylic acid product, which I'll label A for later reference, and an amine, which I'll label B. Okay, so the catalytic mechanism is quite involved. The active site consists of primarily 3 catalytic residues, an aspartate, a histidine, and a serine. There's also a glycine residue, which hydrogen bonds to the carbonyl to stabilize the anionic oxygen in that way. So what happens is our substrate in blue binds here, and the serine is going to act as a nucleophile. So we've got this high effective concentration because it's held close to the amide. So this is going to attack here, but that's going to be accelerated by general base catalysis from this histidine. I'm going to call that general base 1, because this nitrogen is made more basic by deprotonating here with this aspartate residue. So this is another general base. So we get this concerted sort of proton shuttle. The aspartate takes a proton off the histidine, while the histidine is taking a proton off the serine, while the serine is attacking the amide. So that gets us to this tetrahedral intermediate, stabilized by these hydrogen bonds, and then the stuff goes in reverse. So we're going to kick out the leaving group, and that's going to get protonated by the histidine. So now the histidine is acting as a general acid, and that's assisted by the fact the other nitrogen is going to get protonated by the aspartic acid. So again, these 2 residues acting in concert to help with the protonation of the amide, of the amine leaving group. So this is product B, which simply diffuses out of the active site. But what we've got now, this intermediate here, is now an ester, and it's the carboxylic acid product covalently bonded through the serine residue in the active site. This is called the acyl enzyme intermediate. Now, unfortunately, I've made a mistake here. It's correct at the start of the next page, but this should actually be the other protonation state. So this histidine should have a proton over here, and the aspartate should be deprotonated. Okay, so we've cleaved the amide bond that we're targeting, but we need to now cleave the carboxylic acid product from the active site. And the way we'll do that is by going through the same sequence, but rather than using the serine as a nucleophile, we're going to use a water molecule as the nucleophile. So water comes into the active site. Here it is in red. Okay, so I'll do my curly arrows in, I don't know, green. But it's essentially the same sequence. So the aspartate deprotonates the histidine deprotonates the water attacks carbonyl, and then we go back, tetrahedral intermediate, the serine gets protonated by the histidine gets protonated by the aspartate. And we end up back in our original enzyme active site, and as soon as this product A diffuses away from the active site, then another molecule of substrate can come in. Okay, so I've shown you a couple of examples of the types of mechanisms that enzymes use, in particular for hydrolysis. What I'd like to look at for the remaining couple of slides is inhibition of enzymes. Because very often, as chemists, our interaction with enzymes is that we want to inhibit them. We want to make drugs that will specifically inhibit particular enzymes to treat particular conditions. So I'll talk a little bit first about the general character of different types of inhibition, and then we'll briefly look at a couple of examples of inhibitors. Okay, so how can a molecule slow down an enzyme catalyzed reaction? Well, there's various different ways in which this can happen. So firstly, we'll talk about a couple of methods by which reversible inhibition of an enzyme can take place. So if we have a competitive inhibitor, this is a molecule that binds, generally speaking, to the enzyme active site and competes with the substrate. So here's our enzyme, and it can bind either to the inhibitor or to the substrate. Okay, so there's competition for the active site. If the inhibitor is bound, then the substrate can't. So you would expect, in this case, the reaction to slow down. But the point here is that because we've got a competition between these two processes, if we have some inhibitor, we can overwhelm that by putting more substrate in. So by increasing the substrate concentration, we can get back onto this main pathway, and overall the maximum rate of the enzymic conversion, Vmax, is unchanged. So the effect of the inhibition is to effectively increase the Michaelis constant, make the binding weaker. And if we plot that on a Lineweaver-Burke plot, this is what we get for a competitive inhibitor. Okay, so here's the line if we have no inhibitor. And here are increasing concentrations of inhibitor. And you'll remember that the point at which these lines cross the y-axis is 1 over Vmax. So because Vmax is the same, in all cases they all cross the y-axis in the same place. The point at which we cross the x-axis is minus 1 over Km. So as Km increases, as we increase the inhibitor concentration, as Km increases, this intercept gets closer to 0. Okay, so that's a competitive inhibitor. Now, a different way of inhibiting an enzyme is with a non-competitive inhibitor. So these inhibitors they can bind to the enzyme whether or not the substrate's already bound. So starting here from the enzyme can bind the inhibitor or it can bind the substrate. But once it's bound the inhibitor, it can then bind substrate. Once it's bound the substrate, it can then bind inhibitor. But the key is that this enzyme inhibitor substrate complex won't lead to product. So we've got to go through here. And what we find with these types of inhibitors is that the Michaelis constant Km isn't affected, because in fact we don't affect the binding of the substrate to the enzyme. That happens equally well whether the inhibitor is there or not. So Km isn't varied, but Vmax goes down. So this is the sort of Lineweaver-Burke plot we get for a non-competitive inhibitor. So there's no inhibitor here, there's increasing concentrations of inhibitor. Okay, so -1 over Km stays constant. But as Vmax goes down, obviously 1 over Vmax goes up, and so we get this sort of series of Lineweaver-Burke plots. Okay, there is a third class of reversible inhibitor, the uncompetitive inhibitor. These bind to the enzyme only after the substrate is bound, so effectively we lose this portion of the graph. I don't really want to talk about uncompetitive inhibitors. They give a third type of Lineweaver-Burke plot. Okay, so how can we go about inhibiting an enzyme? Well, I mean, there's lots of ways of doing this, and very often there can be a fairly empirical process of screening different compounds. If we want to design an inhibitor, one thing we can do is to take advantage of the fact that, as we said before, enzymes bind transition states strongly. So what we want to do is to find a compound that looks like the transition state, because we know that that will bind strongly to the active site, and ideally it will bind more strongly than the substrate itself. And so these compounds are called transition state analogues, things that look like the transition states of the reaction that's catalyzed and may bind strongly. So here's thermolysin again. Here's the reaction, the first step of the reaction of the hydrolysis. And what we want is a compound that looks like the transition state for this addition of water. And the transition state is going to look very much like the intermediate. So how do we make something that looks like this? Well, we can't just make a tetrahedral intermediate, because tetrahedral intermediates aren't stable compounds. So what we need is something else that's tetrahedral. And effectively, what we do is replace the carbon with something which has a stable tetrahedral form. And the usual thing we can do here is use a phosphate. And so this compound here is a very good inhibitor of thermolysin, because what we have is a phosphonamide which mimics this sort of tetrahedral intermediate. And because the enzyme has evolved to bind that transition state well, then this inhibitor is bound strongly as well. So it's bound by the active site. Okay, so this is a competitive inhibitor of thermolysin. Okay, the final aspect of enzyme inhibition that we're going to look at is irreversible inhibition. So with irreversible inhibition, as the name suggests, rather than having something which just sits in the active site blocking it, we actually have something which will covalently link to the active site. And generally speaking, the way that this is affected is by having something that acts as a substrate for the enzyme, but through the mechanism by which the enzyme normally acts, this compound becomes covalently bound. It doesn't get turned over and released from the active site. And so, I say such enzymes, it's just clearly a typo, such inhibitors are known as mechanism-based inhibitors, or rather more fancifully, suicide inhibitors. I'm just going to give you one example of a suicide inhibitor. And it's an inhibitor of the enzyme acetylcholinesterase. So acetylcholinesterase is an enzyme which hydrolyzes the neurotransmitter acetylcholine once it's served its purpose in your synapses. So this is acetylcholine. And the mechanism by which acetylcholinesterase works is similar to the serine proteases we've seen before. So here we've got glutamate acting as a general base, deprotonating the serine as it attacks the acetyl group. And then the glutamic acid can act as a general acid to protonate that leaving group. And we end up with an acetyl enzyme intermediate. We release the choline, and then this gets hydrolyzed by a molecule of water. Okay, so obviously the tetrahedral intermediate then collapses and regenerates the enzyme, and we get carboxylic acetic acid out. So we can irreversibly inhibit this enzyme by having something which behaves like the natural substrate, acetylcholine, goes into the active site, but then we get to the equivalent of this, and we have something that's not hydrolyzed. And the compound that I'm going to talk about is sarin, which is this red compound here. So this is a fluorophosphonate compound. And it's sufficiently similar to acetylcholine that it will enter the active site and get attacked by the serine oxygen. But now we lose fluoride and get to this phosphonate ester. And this phosphonate ester is a lot less easy to hydrolyze than an acetyl ester that we get naturally. And so this stays here, irreversibly covalently linked, and so the enzyme can't function anymore. And unfortunately, as I suspect some of you are aware, sarin is in fact a nerve agent. It's a chemical weapon, because what happens if your acetylcholinesterase is inhibited, then your neurotransmitters aren't degraded after they've served their purpose in synapses, and so all your nerves essentially get continuously stimulated. Ultimately, it becomes impossible to control muscle movements, including the ones that control breathing and so on, and it leads to very rapid and unpleasant death. So, on that cheery note, that's the end of my final lecture in this course. I'll still see you in the workshops on Thursdays, but enjoy the rest of the course.